Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. In the last video, we almost finished constructing the upload submodule for creating GPU-only D3D12 resources. Today we are going to finish the upload context and then we'll use it to upload geometry data to the GPU. When we create an instance of D3D12 upload context, we need to look for an available upload frame. Remember that the upload frame class is used for synchronizing copy command execution on the GPU with the CPU work that's needed to create an upload buffer and populate it with data. We have got 4 upload frames that can be used simultaneously by multiple threads, so we need to write a function that will find an upload frame that's ready to be used. Because multiple threads can create an upload context, that means that the array of upload frames is going to be accessed by multiple threads as well. To avoid race conditions, we need a mutex so we can serialize access to this array. If you wonder why I didn't put the lock inside the function, the reason is that we are going to access the array of upload frames once more in the upload context's constructor, as you will see shortly. To get an available upload frame, we simply loop through all frames and take one that's ready for upload. In case all upload frames are in use, we can use a busy wait loop until one of the frames becomes available. I'm not a fan of busy waits, but this is a low contention code path and the chances of wasting a lot of CPU cycles here are not that high. However, it would be a good exercise to try using a condition variable here. When we have the index of an available upload frame, we need to mark it so it can't be picked up by another thread. I can do this by simply giving the upload buffer pointer a non-zero value, since isReady function looks at this pointer to figure out if the frame is already being used. We could have written this part in the getAvailableUpload frame function, and it would have been totally okay to do so. I chose to keep it apart because marking a frame is not the responsibility of the function that gets it, if that makes sense. Now that we have an upload frame, we can use createBuffer function to create an upload buffer for that frame. I know I made this data pointer optional in the last video, but I'd like to revert that. That's because we need to give it a null pointer anyway if we want to also set the isCPUAccessible parameter to true. We can also give the created upload buffer a name. I'm kinda abusing the indexed macro here to append the size of the created buffer to its name. Next, we need to ready the upload buffer by mapping it to system memory. The user of this upload context can then write whatever data they have to the upload buffer. We also expose the upload frame's command list, upload buffer resource and its CPU address through accessors in the upload context class, because we need them to write data to the buffer and record copy commands. Finally, we reset the command allocator and command list so that they are ready for recording commands. To summarize the resource upload so far for GPU-only resources, We call create buffer with the initial data that needs to be on the GPU and set is CPU accessible to false. Then a committed resource is created that will eventually contain the data. Because we have data and it's not CPU accessible, an upload context is created that provides us with an upload buffer to which we write our data. This upload resource is then copied to the GPU-only resource using a command. Please note that createBuffer function is now a recursive function because it's again called from upload context's constructor. The copy command will be executed when we call endUpload, which we are going to write next. First, we assert that the frame index is valid, and then we take a reference to that upload frame. We need to close the command list before executing it on the command queue. We have already seen how command lists are executed, which is done by calling execute command lists function of the command queue. The upload command queue is the same, except now it could be called on different threads. Although calling execute command lists is thread safe, I would like to make the synchronization using fence values and signals simpler by just serializing this part as well. This is again done using a lock and a mutex. I don't think it would pay off in terms of performance to really make this part thread safe, and to be honest, this is as much as my brain can handle at this point. So feel free to improve if you're up for a challenge. Similar to the graphics command queue in the renderer, we increment the fence value and signal the fence with that value. In wait and reset function, we check if the completed fence value of the upload fence is greater or equal to the frame's fence value, and in that case we know that the command list has been fully executed. When the upload is actually completed, we override the member data in upload context with invalid initial data so that it can't be used again. I'm a bit lazy, and instead of setting all member variables individually, I'll use the placement new operator and a private default constructor to overwrite all data at once. This is a debug build only operation. This concludes the upload submodule. In order to plug it in the low-level renderer, we need to initialize it when we start the renderer and shut it down when the renderer is shut down. As you can see, we are still able to run the test application. In the output panel, we can see that upload command allocators, command lists, and command queue were all created successfully. Now let's write some code that actually uses the upload submodule to put some data on the GPU. I'm going to add a new header file in which we declare functions that upload assets to the GPU. I'll call it d3d12 content.h. Here we'll add a namespace for each asset type. The low-level renderer doesn't care about any kind of mesh hierarchy, such as groups of submeshes and LODs. It simply uploads individual submeshes to the GPU and puts the resulting resource pointers and buffer views into a flat list, as we'll see shortly. Because ultimately asset data will be loaded from files, we'll accept raw byte pointers to the data. We do expect the data to be in a correct format, which I'll describe in a minute. Let's add a CPP file and implement these functions. As I mentioned, we need mesh data to be in a certain format. We don't care where this data comes from, as long as it has this format, we are good. I'll use pseudocode to describe what data we can expect. So this data pointer points to a block of memory that contains data for a single submesh, and we expect to encounter the information in correct format in this specific order. The element size for vertices, vertex count, index count, elements type, primitive topology, position buffer that contains vertex positions, element buffer that contains other vertex elements, and finally the index buffer. If you're wondering what any of these fields mean, make sure to watch the videos about geometry assets where I pack vertices using a specific format. Please also note that we are passing a reference to the data pointer so that we can advance the pointer with the number of bytes that we read from the buffer. If you prefer not to have this side effect on data pointer, you could pass the pointer and return the number of bytes that we read in an integer output parameter. Because we are going to read a raw buffer, we can use the utility class for reading blobs of memory. Then we simply use it to read each field. We can determine the size of indices, that is, whether they are 16-bit or 32-bit values, from the number of vertices. We can also calculate the length of each buffer. The length of position buffer is the size of a 3D floating point vector times the number of vertices. Similarly, the length of element buffer is the element size multiplied by the number of vertices, and the length of index buffer equals the index size times the number of indices. Remember that vertex elements are optional and therefore the element buffer might be empty. Now we are ready to upload these buffers to the GPU. We can use the createBuffer function to upload each buffer separately, but we can also upload all of them using a single buffer resource, and that's how I am going to do it. Because we are going to use GPU addresses that point to an offset within this buffer resource, we need to make sure that each pointer's value is aligned to a multiple of 4 bytes, as required by the API's specifications. The position buffer will be aligned automatically since it has the same start address as the buffer resource. Buffer resources in the 3D12 are created with 64 kilobyte alignment, which makes them also aligned to any smaller number that's a power of 2. To get the aligned size of the buffer resource, we need to calculate the aligned size of position and element buffers first. Let me also put this alignment constraint in the function's documentation. I don't expect this to be a problem if the data is being loaded using some other API, like Vulkan, since these kind of alignment requirements are imposed mostly by the hardware, so I'd expect different APIs to have similar requirements. And if not, one can always copy the buffers to get rid of the padding that happens when we align buffer sizes. To calculate sizes that are a multiple of some alignment value, I'm gonna add 2 new template functions in math header. One for aligning up and one for aligning down the size that is given. To align a size up, we first assert that the alignment is non-zero and a power of 2. Then we add the mask to the value of size and clear the mask bits. Checking if an integer is a power of 2 is pretty simple. We know that binary numbers greater than 1 have a single bit set if they are a power of 2. The fastest way that I know of to check if an integer has a single bit set is to first subtract 1 from it and then logically AND it with their original value. We are already asserting that alignment is non-zero here, so we only need to check if a bit is set in the second assertion here. Align size down is the same, except now we don't add the mask value, we only clear the mask bits in the size value. Now we can use align size up function to compute the aligned buffer sizes for position and element buffers. We add all buffer sizes together to get the total size of the buffer resource that we need to create. The buffer is also initialized with the data, pointed to by the current read position of the blob stream reader. Because we already read the buffer data, we need to move the current read position within the buffer by calling skip. Now, the beauty of it all is that we are using the upload context and copy queue without even knowing it. When the buffer resource is created, that means that we successfully uploaded our mesh data to the GPU and it's pretty much ready to be used for rendering. When we would like to render a submesh, we need to provide the pipeline with the location of our mesh data within this buffer resource. Therefore, I'm going to define two data structures, first of which contains information about the position and index buffers. The second structure contains information about the element buffer, elements type, and primitive topology. I should probably fine-tune what goes where with regard to cache coherency and data sizes, maybe in the next video. First of all, we need to remember our buffer resource pointers, so let's put those in a free list. We also need a list of position views and a list of element views that point to the buffers within the GPU resource. For the position buffer, the buffer location is the same as the start of the buffer resource because it's the first buffer within that resource. So we simply call getGPUVirtualAddress function to get its location. Size in bytes is the position buffer's size. Make sure to use the unaligned buffer size because that's the real length of the buffer. Stride in bytes is the size of a position vector. The index buffer is the third buffer within the resource, so we need to offset its location by the aligned sizes of the position and element buffers. Index format is determined by index size. Direct3D supports 16-bit and 32-bit indices, and we use the index buffer size for size in bytes. If we have vertex elements other than position vectors, we'll fill in the element buffer view. Because the element buffer is the second buffer, we need to offset its location by aligned size of the position buffer. Size in bytes is again the element buffer size, and stride in bytes is element size. Next, we set the elements type and primitive topology. This 32-bit value for primitive topology that we read from mesh data is an API-independent value because the mesh data is not packed for a specific graphics API. So we need to convert it to a D3D12 primitive topology enumeration. I'll work on that next, but let's finish this function first. Because loading assets may happen on different threads, we need to lock the free lists as they are not thread safe. So let's add a mutex just for adding and removing submeshes. Then we can lock our data right before we are going to modify them. Now to define an API-agnostic enumeration for primitive topology, I'll add a new header file with functions and data types which are going to be handling content in a way that's API-independent. Here we can define our primitive topology enumeration. Now we need to convert this value to its directx equivalent. I'll write a function that does this conversion. It's a simple switch statement that returns a D3D primitive topology value. Now we can write the remove function which unloads submeshes from the GPU and removes the corresponding data from the free lists. Again, we lock the function to avoid race conditions, remove the buffer views, and finally release the buffer resource. To call release, we need to include the 3D12 core header file. Note that we are using deferred release function because the GPU might still be rendering this object. We also remove the resource interface pointer from the free list. Awesome! This concludes the episode about uploading data to GPU and using the upload context to create GPU-only resources. Thank you for joining me today. I hope you enjoyed watching this video and I see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub so you don't have to type everything over from the video. Plus there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!